Okay. Okay, so good morning, everyone. And what I'm going to do here now is to review the topics that we covered in 2012 throughout the semester. And there are a couple of points of emphasis. You will see what I want you to know by heart and what are some of the other things that I need you to recognize, but you will be given enough information if you need to address it. All right. So let's go. So the main topics that we covered this semester were power supplies, operational amplifier applications, oscillators, active filters, digital to analog interfacing, and we had a small lecture on 3 or 4 little things there, and then the environmental impact of electronic devices. So in terms of power supplies, shift this a little bit. In terms of power supplies, we started off and we spoke about these topics here. Rectification, unregulated supplies, regulated supplies, and the two sort of categories that we looked at were the shunt regulator and the series regulator. The shunt regulator is the Zener diode. Remember what the shunt regulator is that the regulation or the controlling element is in parallel with your load. And the series regulator, where you use a device that is in series with the load. And the typical devices are a pass transistor, which might either be a single junction transistor or dual transistor that we also know as a Darlington pair. So in the sort of yellow box there, right, I want you for this particular topic to be able to draw all of the circuits except any circuits with integrated circuit regulators. We'll come to that in the next slide, right? So I need you to draw anything related to like half wave or full wave rectification. There were 3 versions that we looked at, one using 1 diode, one using 2, and one using 4, right? I need you to calculate component values based on data that is given, and for any circuit to calculate all the voltages and currents. Okay. And then we expect in the case of the regulated power supplies, we look specifically at a type of regulation called series feedback, and we introduce the concept of the error amplifier. Let me get a pen here, right? We introduce the concept of the error amplifier here, and there are 2 ways you can implement the error amplifier. One is a simple transistor, and the other one is using an op-amp. And then the topic on regulation, we ended by talking about the integrated circuit regulators. And we looked at some examples of positive and negative voltage regulators, either constant voltage or variable voltage. And there were some part numbers that were given, right? I need you to be at least to be familiar with what the regulators, how they operate in terms of a block diagram, and how they compare to the sort of standalone regulators that we discussed before. And then the last topic on this that we looked at was that having made a power supply, now you have to protect both the power supply and your load. And we do that by 2 sorts of overcurrent protection. One, which is simple overcurrent protection here. That's the one where you put a small series resistance in line with the series regulation element, whatever that happens to be, or the other version called a fallback regulator. The difference between the 2 of them is that the simple constant current overcurrent protection, it sets the current up to a maximum, and then the power supply will basically keep pumping that into even up to a short circuit. So what you have is that the pass element, like the pass transistor, for instance, if you remember how the pass transistor works, you have the unregulated voltage here on this side, and you have the regulated voltage on this side. Okay, if you happen to be short circuiting it, it means that what happens here is at 0 volts, here is at whatever it is, let's say 10 10 volts for argument's sake, and then you are supplying the short circuit current limited by that little resistor that you have in series here. So that the regulator itself has to pass I squared or sorry, VI, which is the voltage across here, multiply by that current. So it dissipates a lot of power. So what we do instead is that we introduce another element. We added two more resistors and we created something called fallback. And what that does is that as the power supply goes into its constant current mode, it reduces both the current and the output voltage at the same time. So you end up reducing the amount of power being dissipated in the pass element. Okay? And remember, I mentioned in the discussions that the choice of this little the series resistance is usually less than 1 ohm. Okay, and you have to be careful with choosing it. If you choose it too big, then you don't get an adequate voltage drop across the pass transistor to make it work, and the system will not work. But all of the configurations I need you, and you saw it in the problem sets, and you saw it in the midterm, that I need you to be able to draw the circuit, all of the configurations, or if I give you the configuration, to be able to calculate all of the voltages, currents, and if required, resistances in there, and to make the assumptions. Okay. All right. The next topic that we went on to were the operational amplifier applications, which in a general sense is really everything else in the course, but we categorized it specifically. We looked at comparators and level detectors, which were circuits that if you have a particular voltage, either positive or negative voltage, that you could use the op-amp in its open loop configuration. In other words, no feedback. And once you detect the output, the input, either positive or negative voltage, then the output of the comparator or the op-amp, which is set up in that mode, will either go to the saturated positive or saturated negative supply. And then if you put a reference voltage at one of the two inputs, then you can have it detect a particular reference voltage. One variation we saw was that if you have noise on the level, so let's say this is a level that you want to detect, but unfortunately, the level itself has a lot of noise associated with it, then what would happen is that the comparator would switch, instead of reaching the particular reference level that you have, every time the noise crosses that threshold, the comparator would switch at the output. So to avoid that, we put a certain amount of feedback on it, and we created something called the comparator with the hysteresis, or the more common known name is the Schmitt trigger, SCHMITT, right? A Schmitt trigger, which is a comparator, but the comparator has feedback. And what you basically do then is that if you have your detection voltage, this is what I wanted to detect, I establish, you could get a different color here. I establish a little two thresholds around that, right? A V upper threshold and a V lower threshold. And the comparator will only trigger at these particular points. So if there's noise inside of here, right, it will ignore the noise and only trigger when you pass the upper or the lower threshold. Of course, you have to adjust it based on the particular application that you're dealing with. And that's a practical consideration that will only happen when you are actually designing something for an application. All right. Then the next topic we moved on to was differential amplifiers. Remember the differential amplifier, what you're looking for is that if I have some load, what I want now is to measure the voltage across the load, right, which is the differential voltage. I am not concerned with whatever the voltage at the opposite ends of the load are, the absolute voltage. I don't care too much what V1 or V2 is in this particular case. What I am concerned about is V1 minus V2, the difference. And that's where we have the differential amplifier. And we saw the circuit there. I need you to know how to draw the circuit, of course, how to, what are the values for the feedback on ground resistor, what what do you call it? The configuration looks like. And we saw that the differential amplifier, it works well, but there's what we call V1 and V2 are common mode voltages. These are the common mode voltage, and this is, of course, a differential voltage. What we want to do is to ignore this and amplify that. How good the differential amplifier does that is by a particular characteristic called a common mode rejection ratio. Plain English, common mode rejection. So it wants to reject this and amplify this. So the bigger the common mode rejection ratio, the better the differential amplifier works. The unfortunate thing is that the differential amplifier requires matched resistors. If you remember, there were two resistors, a feedback and a ground resistor, and two input resistances. If they are not matched to less than 1%, then the common mode rejection ratio, which is the one in circuit, is worse than what the amplifier comes with. So if you buy your op-amp, for instance, it comes with a value on the data sheet that is known as the extrinsic common mode rejection ratio. We said because it's a large number, they typically specify this in decibels. So like a good quality op-amp might have a common mode rejection ratio of 85 decibels. But when you put it in circuit, if you use things like 5% resistors and so on, this 85, and we did an example in class, this 85 dB could drop to as low as 30. Right? Because you're dealing with a log scale, that is a significant reduction in the performance of the device. And what it means is that it will actually be amplifying V1 and V2 as well as VDIF. Okay? And the example we looked at, one of the things we spoke about, if, for instance, V1 and V2 are line voltages, let's say 120 volts, and you run this to your differential amplifier, right, somehow, then what happens is that because the common mode rejection ratio is not good as a consequence of the mismatching of the resistors, the circuit is going to try to amplify 120 volts. Right, and 120 volts, I mean, if you're operating at plus or minus 12 volts for a simple op-amp, it's simply not going to work. So what you're going to now suddenly get is that the output will maybe go up to V plus VSAT, as high as it can go, and stay there. Right, so that is one of the reasons why this specification is so important. All right. So to get around that, we saw that there was a little variation that you done and I'm expecting you to know how to do that, that you took the differential amplifier, which was the one with the 4 resistors, looking like that. Right? So you have that. And then at the input here now, we added 2 more op-amps. Okay? And we put in the input to the non-inverting. The differential input is going to the non-inverting input of the 2 op-amps. And then between these 2 op-amps now, on the 2 inverting inputs now, we have a resistor here. And then we tie this back to the output. Okay? And then you wire it up. So you now need to know, well, this is a gain resistor. You need to know what is the relationship between the gain and these 2 resistors here. You also need to know what's going on with these 4 resistors here. Right? Of course, the notes have them notated, labeled a little bit differently. Again, one of the things you need to be able to do is to draw it and to label. If I give you it labeled like this, and not using the RF and RG, what do you call it, symbols that we used in class, that you could still recognize that this is an instrumentation amplifier. Derive the gain equation for this, and list the advantages over the basic differential amplifier. The biggest advantage, of course, is that you only need one resistor to control the gain. And the second one, of course, is that you don't need to have these resistors. Once they're equal, right, then everything is really largely dependent on the two input amps. And of course, it has a high input impedance because we are sending the signals to the non-inverting input. Okay, so you need to draw the circuit just like the previous one here, right? Draw the circuit for the differential amplifier, derive the gains, the common mode and the differential gain, right? You need to define common mode rejection ratio, which is AV diff over AV common mode. And as you could see just by this, so this is CMRR, right? This is the raw number. If this is small, then this number is going to be big. And of course, to convert it to decibels is 20 log to the base 10 of this number here. Okay? And of course, you could go back and forth between them. So in both cases, I need you to be able to draw the circuits, derive the gain equations, and calculate the various values going on in there. All right? Then after that, now we started to look at some circuits called precision rectifier circuits. Precision rectifiers were needed because a normal diode needs 0.7 volts approximately, right? It actually varies between maybe 0.5 and maybe 0.9, depending on the model of the diode itself. You need that amount of voltage to turn the particular diode on. So if you happen to have a signal that is less than that, a small signal here, and the peak to peak is maybe 0.1 volts, and you need to rectify that. You can't simply use a plain diode. What we need to do now is to put some op amps around the diode, have the diode in the circuit, and what happens is that the op amp itself takes care of this 0.7 volts for us. Okay? I need you to be able to explain why you need these circuits, which is what we just spoke about here. And I don't expect you to be able to draw the circuits, but there were a couple of versions that we looked at, and I need you to be able, if I give you it, to decipher what it is. There was a half-wave inverting version that we looked at. There was a polarity separator version that we looked at, and there was a non-inverting high impedance full wave version that we looked at. So in all three of them, I need you to be able to, if you look at the circuit, to say, right, okay, this is the half wave, this is the full wave, this is the inverting or the non-inverting one, and then to explain the operation. So if I give you a circuit, you would see that in a couple of the past papers as well. If I give you the circuit and tell you, well, okay, such and such is the input, let me know what the output is going to be, okay? Or in this particular case, if I give you a sinusoidal input and I ask you, well, draw what the output going to look like, then you need to be able to do that, all right? And then we looked at waveform generators. These basically that we were looking at, and we are distinguishing the waveform generators from oscillators. All right, the waveform generators are the particular types that we looked at were ones called multivibrators, and there were three types that I gave you. Not expected to be able to draw, but again, like the precision rectifiers, if I give you it, you need to be able to explain how it works, know the equations, and calculate some values to give the particular performance that we want. The three that we looked at were they are stable, right? That's basically, like some people pointed out, a square wave generator, if you like. Right? The monostable, which is the one that it stays in a particular state, and then when you do something to it called triggering, it went to the other state, stayed there a particular time, and then returned to its stable state. This is what we are interested in. It is basically a circuit to give you a single pulse of a particular time duration. We spoke about, and one application was like the power on reset for circuits. That when you start the circuit, many circuits, you need to make sure everything in the circuit is at the same voltage level, or memories are cleared, and everything is at the zero state. So you would use a power on reset. And to do that, you need a pulse of a particular time. This is one way of doing it. The multivibrator is to give you a square wave signal of a known frequency. So if you need a square wave of some particular frequency for some application, right? Counting applications, clocking applications, for instance, then that is where a stable comes in. A stable means it's not stable in any state. And then the last one was the bistable or the flip-flop. That one would stay either plus VSAT or minus VSAT indefinitely. So once it goes there, it stays forever until you trigger it. Okay, and there are applications for that, for instance, turning on or turning off particular devices, or versions of it we spoke about in digital circuits. They use that as the basis for memory elements, because if it will stay in a particular state, you can use that to record zeros or ones. And I mentioned that devices like the field programmable gate arrays have huge quantities of these bistables or flip-flops in them. And that is how we create random access memory. Okay? So again, know the equations, right? Know how to calculate the output. In the case of the astable, in the case of the monostable and the astable, there are a couple of relationships between the resistors on that set the upper and lower threshold, which are the switching points and so on. Once you know that, then everything else falls back from that. Okay? And then, of course, draw the output waveforms in a label diagram. When I tell you to draw a label diagram, it means that if you draw something looking like this, you need to tell me that the output here is at VSAT, right? Plus VSAT, that here is minus VSAT, what this time interval is, right? Label the axis in time, in seconds or milliseconds or microseconds, whatever it is, okay? All the pertinent information, that is what I mean by a label diagram, all right? Anyway, we'll talk a little bit about some exam technique in a while. Okay, and then on the other waveform generators, we looked at the single ramp. Okay, this one is an easy thing. Learn to draw the circuit, explain the operation, and draw the output waveform. Remember, this is an integrator. So all it does, it gives you either a ramp going this way or a ramp going that way. This was the circuit that we looked at, the negative going ramp. And then the triangle wave was that you combine the single ramp generator with a Schmidt trigger. And then what it does is that it ramped up and it ramped down, up, down. So you get a triangle wave. This basically, the principle of this is the operation that if you integrate a step, right? If you integrate a step, you get the ramp, right? Which is something that you learn from your signals and systems. So this circuit is an integrator. And when you put a step input, it integrates the step and gives you a ramp. And of course, the ramp can't continue indefinitely. It starts at minus VSAT and will stop at plus VSAT, okay? For all the op-amp circuits, if I don't give you that information, then whatever is VCC, it's a safe assumption that like for the 741s, that VSAT, the two VSATs are about VCC minus 1 volt, okay? So if this is 12, if this is 12 volt, then plus or minus VSAT will be about plus or minus 11, okay? Remember that. That is your assumption, or I will give you it, right? I have no issue. If I didn't give you it and you make a reasonable assumption like that, then you get the marks for the question, okay? And the triangle wave, well, we just spoke about the triangle wave. So these two go together, right? This one is the integrator. And this one is the integrator and Schmidt trigger. Okay? Right, and then we went on as a little distinction. We now looked at a type of waveform generator specifically called an oscillator. The oscillators produce an output that is sinusoidal. And we looked at how it worked. First off, we did a short review of block diagrams, and this particular oscillator, the oscillators use positive feedback. And as a result of that, we saw that if there were certain conditions, namely that the gain is 1 and that the phase shift with 0 degrees or multiples of 360 degrees, or as I said, 0 or multiples of 2 pi radians, then what happens is that the feedback, the positive feedback, basically produces a circuit that can, once it starts running, it will continue indefinitely. And we call that those sets of conditions the Barkhausen criterion. And you will see it in the past papers and in the problem sets. Whenever there's an oscillation question, one of the things you need to figure out is what is the situation that will satisfy the Barkhausen criterion. In other words, what will make the gain 1 and what will make the phase shift of the transfer function a multiple of 2 pi, right? N equal to 0, so it could go from 0 to 2 pi, all right? And we looked at, in specific, we looked at RC oscillators. Those were oscillators that only require a resistor and a capacitor. The first one was the Weinberg, right? I need you to be able to look at the circuit. If I give you the circuit, to identify what it is and to derive the transfer function, derive the frequency of operation, and the gain. All right? And in all of the cases, what I told you is that once you get a transfer function, right, A plus BS, right? So let's say you get the transfer function, H of S is equal to something looking like 1 over A plus BS. Then the first thing is to convert this into its frequency form. So you get H j omega is equal to 1 over A plus j omega B. Okay, and then from this now, you need to get the magnitude of H of j omega. And for that magnitude now, what the magnitude and phase, sorry, what value of omega is going to make the phase of this 0? And remember what we said, the phase of this, remember, is the inverse tan of the B over A. It's a normal complex number. So to get this as a multiple of 2 pi, 0 or 2 pi, it means that some value of omega has to make this section 0. And you solve for it. That is how you get the frequency of oscillation. And then when you substitute back that now into the original equation, you're going to see a gain, like in the case of this, the Weinberg, you're going to see a gain come up of a third, right? And then, so if I have to satisfy the Barkhausen, I need a gain of 1, so that somehow along this, the Weinberg circuit has a gain of a third, so I have to attach something to make the gain 1. In other words, I have to attach an op-amp circuit whose gain is 3. All right? So we looked at that. And then we looked at the two other versions of it, which was the phase lag and phase lead. And remember the difference in them. In both cases, there are 3 resistances and 3 capacitors. All right, so one looks like this. Right? And in the other case, the R's and the C's are swapped. So you have the resistors going to ground and the capacitors in series. So if I give you them, I need to identify which is the lag and which is the lead circuit. Okay, and if necessary, draw this alone. Draw the lead or the lag circuit, just the resistors and capacitors. Okay, once you do it now, memorize the transfer function. One of the problem sets ask you to derive it. I think just for getting used to it. And what I told you all is that if you derive it once, it's going to stick. Okay, but for the exam, I'm not good because it takes a long time. It's a couple pages of some manipulation to do. But if you do it once, you'll remember it. But however you want to do it, I need you to memorize the transfer function. and from that, derive the frequency of oscillation, right, which is substitute S equal J omega, and then find a value of omega that makes a transfer function phase 0 or 2 pi. In this case, the phase is 180, right? So you need to find out what value of omega will make the phase, in this case, pi. And then once you have that now, and you substitute, once you solve for omega and you substitute it back into the equation, you're going to get a gain. And this now, the gain will tell you that the op-amp circuit that you're going to put around this, right, what the voltage gain is going to be for it. If you remember, the gain is going to be something like minus 29 or plus 29. All right. And then the last one that we looked at was the multi-phase oscillator. That one uses 3 op-amps. The previous 2 use a single one. This one uses 3. And now, again, if I were to give it the circuit to be able to get the to identify what it is, in this case, because it's so simple, you should be able to derive the transfer function. The op-amps basically separate the unit into 3 parts. So the transfer function is really the transfer function of 1 part cubed, all right? And from that, of course, you should be able to get the frequency of oscillation and of course, the gain required. All right, if I recall the gain, I think for this one might be something around 8. Don't hold me to it. All right, and then crystal oscillators, I give you for information only, we did not do, right? So for those of you who short on revision time and want to sort of spot topics to cover, you could ignore this, okay? There will not be a question on this, but this is good when you're going to do micro-P next semester. You're going to bounce up these things, and it is good information to keep in the back of your mind. And the last thing on this we spoke about was output stabilization. We said that unfortunately, when you start the oscillator is going to do something like this. And then when it reaches VSAT or so on, eventually what you start getting is this coming out. So to avoid this happening, what we need is, as the gain starts to get close to when you saturate the op-amp, we need to have something called an automatic gain control that will back off the gain a little bit. Remember, the gain is supposed to be 1, but to get it to work, to get it to start, the gain actually has to be a little bit greater than 1. And once this circuit starts to oscillate, you reduce the gain. And there are a couple of ways of doing that, and we mentioned them here. One is to use a thermistor. A thermistor is a device where as the temperature goes up, the resistance goes down. The sensor is something like a small light bulb, a battery-operated light bulb, that when the temperature goes up, the resistance goes up. So either of them you can use in the feedback, the gain control for the amplifiers. Or what you could do is if you put the Zener diode in the output, right? And what we did was to use 2 Zener diodes in a configuration that we call a back-to-back operation like this. So you wire up the Zener diodes like this. And what happens is that if you, for instance, if I go on here, this now will clamp the positive and negative voltage according to whatever the Zener diode is. If it goes positive, it will forward bias. It will forward bias this and reverse bias this to VZ. And if it goes negative, it will reverse bias this and forward bias that. So it clamps the output to whatever VZ happens to be, and you can limit it. I don't need you to draw any circuit diagrams, but if I ask you a question, why do you need amplitude stabilization? You're going to have to tell me the business about the gain and what happens as the gain changes and why. Okay? Then the last main topic we looked at were active filters. And there were 4 types of active filters, 4 categories I need you to identify and to draw the ideal response, right? So there were the low pass, the high pass, the band pass, and the band reject, or the notch filter, and what the ideal response is. So like the ideal response for a low pass filter is that it will pass everything up to some cutoff frequency and then stop. And this is the cutoff frequency, either omega C or FC. You could draw it with either one, either in radians or hertz, right? The choice is up to you. So this is the pass band. The normal pass band gain is 1, and the low pass filter cuts off. The high pass filter, of course, does the reverse. All right, so the high pass filter will do something looking like this and then go up. So this will be the FC for the high pass filter. The band pass filter, of course, passes a band of frequencies, and the band reject or the notch filter, right, rejects a band of frequencies. Okay, so in both of these cases, there are two frequencies. There's a lower frequency here, and there's a higher frequency that needs to be specified. Okay, I need you to be able to look at the circuit, right? Draw the responses, derive the transfer functions of the first order low pass and high pass. Okay, remember one, again, it's a simple, the first order has one capacitor and one resistor. Right, so the low pass looks like that. The high pass, you swap the resistor and the capacitor. Okay, and then you need to specify what the real performance looks like. And you remember this, you would have done some of this in ECNG 2011, and we did it here as well. Okay, in the case of the second order filters, the second order low pass and high pass, we looked at a particular version called the Salin-Key version. That one had an additional resistor. Because it's a second order, it must have an extra capacitor in it somewhere, right? The capacitors are what create the order of the filters. I do not want you to memorize the circuit, but you can, if you were to encounter the circuit, to recognize what it looks like, but I need you to memorize the transfer functions. And again, derive the cutoff frequency for all of them. So both the first order and the second order filters, and to sketch the response. The roll-off rate for these is 20 dB per decade. The second order filters, of course, roll off at 40 dB per decade. A third order would roll off at 60, and so we went on. Okay. And then we saw that we could make now band pass and band reject filters by cascading or wire or connecting first order sections in series. We actually did that here as well too. All right, we did this, I didn't have it on the slide, but we also did, instead of the second order Salin-Key version, we saw that you could take, if I take two first order low pass filters, right? So this is a low pass filter, Both of them have the same cutoff frequency. If I cascade them like this, then what I create is a second order low pass filter. Okay, the difference between this and the Salin-Key uses one op-amp. This version requires a second op-amp. And of course, if I put another one here, right, I create a third order. And if I put another one, I could create fourth, and so I could keep going on. So I could keep adding first order sections in cascade. All right. And then we saw now that we could make, using the same approach, we could make band pass and band reject filters. So by cascading a low pass and a high pass, I could create a band pass. And by putting a low pass and a high pass filter in parallel, we can create a band reject or a notch filter. Okay? And I give you the transfer functions, and you know how to derive them, right? They're easy because each of them are independent op-amps. So all you have to do is to either, if they are cascaded, you multiply the transfer functions, and if they are parallel, you add them, right? So in each case, know how to derive the cutoff frequency for it, right? The cutoff frequency is, again, just to remind you, HS is what you would come up with. From HS, you go to HJ omega, and then from HJ omega, now you look and see the value of omega that makes this 1 over root 2, or 0.707. Okay? So you calculate that, and then from that now that will tell you what the cutoff frequency for the particular type of filter you're designing. Okay, and then sketch the responses. Of course, the ideal bandpass is one thing, but the real bandpass filter gives you a sort of characteristic like this, and the notch filter or the band reject filter gives you something looking like this. Okay, and it's up to you to sort of identify which is which. And they're all in there were examples, and I had diagrams in the slides showing what the performance would look like. I needed to explain a little bit, if required, what is the importance of phase. We spoke about phase. Phase is a distortion, and it causes certain types of behavior. Okay, you correct it by using a particular type of filter, but we did not talk about that, so you don't have to worry about the all-pass filter, right? So you could ignore this, right? But understand this. Okay? And then the two other side topics that we looked at, those were the main broad areas. And then we looked a little bit about when you have to connect the digital and the analog world. And we spent some time talking about analog to digital conversion. Specifically, we spoke about sampling. We spoke about a sample and hold circuit. Okay, so the zero order hold, remember, it's something looking like this with two op amps, right? A storage capacitor here and a switch, right? So you have in and you have out, right? And what happens when you close the switch? The capacitor here basically follows the input voltage. When you open the switch, the capacitor stores the value. Okay, so that's the sampling and the holding. And I need you to be able to draw the circuit, explain how it works, okay? And then what is aliasing, which is connected to this. Whenever you have a signal, if you have a signal and the signal has the highest frequency component of it is Fs, then you have to sample at least 2Fs to avoid something called aliasing. And what is aliasing? We did it graphically. Aliasing is the creation of frequency components that were not present in the original signal. So if I had a signal like Fs and I didn't sample it at 2Fs, then what is happening is my sample signal, apart from Fs, is going to have some additional frequency components that were not there originally. They are called aliases, and they will cause issues in the particular application that you're dealing with. Okay, so you need to know what is aliasing and what, given a waveform, what is the Nyquist sampling criteria, what does that mean, and what would be the sampling frequency to use. Then we spoke about this thing that most of the op-amp circuits that we dealt with needed the op-amp to be connected to plus VCC and minus VCC. But there were applications where you only have the plus VCC. If you just simply grounded the negative supply for the op-amp, it simply does not operate between 0 and plus VCC. Okay, because of the VSAT requirement, it actually will not go close to 0. It will be some voltage above, and then it wouldn't get close to VCC. It will be some voltage, some volt below that. Like in the case of a 741, it will be 1 volt. So if I were to simply put a 5 volt supply here, if I take my 741 and connect it to a 5 volt supply, and I'm assuming that this now is going to some digital circuit, right? Unfortunately, just wiring it up here, the op-amp is going to run between 1 and 4 volts, right? So 0 volts in will not produce a logic 0 or 0 volts coming out, and 1 volt in or 5 volts in will not produce 5 volts coming out. They're going to get 4, and the digital circuit can't interpret that. What you need are special op-amps designed for single polarity, or what they sometimes call single-ended operation. And you have to go and check the spec sheets and pick a particular op-amp that will give you the op-amps that are designed for that. So when you put it in here, a 0 will give you a 0, and a plus VCC will give you a plus VCC coming out. Okay? And then the other thing that we spoke about here was something called effective full-scale range. Remember, when you convert from analog to digital, there are a number of bits that you're dealing with. So for instance, if you're dealing with 3 bits, then the voltage level is now converted to 8 levels. Right? 4 bits will give you 16, 5, and so on. So in other words, n bits give you 2 to the n levels. And when you put in the full scale on the input, you're going to get 1 level less. So like, for instance, 3 bits is actually counting from 0 to 7. 16 bits is counting 0 to 15. So the output voltage level is 15 times whatever is the individual step change. Okay? And that is what we call the effective full-scale range. So it's actually 1 bit less than whatever you think it should be. And you need to be able to calculate that. It's a simple calculation. Okay? And then we spoke about some environmental consequences of electronic devices, and spoke about, well, generally e-waste. And you need to know about the ROHS compliance, what it is and why it is important, our local versions of it. So you need to, I gave you an example, but you need to go and just check out what the local versions are. And then the last thing had to do with what is the Basel Convention relating to that, and who are the people in our part of the world, in our region, that are responsible for advising on the implementation of that. Okay, it's a discussion topic, English, no sort of maths, no circuits to draw, anything else, but it's something to read and recall. Okay, and that was the topics, or were the topic lists for the semester. So let me just stop this here, and let me see now. Are there questions? Let me stop this here and have a look at the chat here. So any questions? Now are the times to ask the questions. Let me hear. Anything that you thought I covered and that I didn't mention here, or anything that you want to double check to make sure that we covered it or not? Anybody? Nothing?
Is environmental impacts coming for exam?
Yeah. Well, it's all of the
Okay.
topics. Any one of those topics that we looked at could be coming for the exam. Okay. So just
Okay.
double check it through, and you will see what what you have to know. Just what I mentioned on the last slide. And you will see it in the last past papers as well, what kind of question could be asked on that. Okay. All right. The revision problem set that I put up for you all to do, with the solutions, notice that I put some problems on the older past papers. I told you which ones you could attempt and which to ignore. Right, there were some topics that used to be covered that we haven't been doing and we're not going to do and we did not cover this semester, so you could ignore that. If it's not on what I just gave you all on this summary slide, then you don't have to worry about it coming in the final exam. Yeah? For first order low pass filter, it is okay. So to answer that question, Anish, it is a decaying, right? Remember the first order is cutting off. So if it's cutting off, it means it's a decaying response. So you answer it is plus 20 or minus 20. Minus 20, good, right? The high pass filter would be the one with the plus 20. Okay, the band pass will have both a plus 20 and a minus 20, or for higher orders, of course, they both the plus and minus, like the band reject as well. Okay, any other questions?
So would you be going over the method?
Yes, I put up in the chat on the announcements yesterday. I put it up so let me see if I have the timetabling here. I think what I said is that's not got it written down here for you. Right. So next week, Tuesday, which is the 26th, we're going to have an online session, and I'm going to go over the midterm and problem set 3, any issues with that, and start looking at any questions or concerns people might have with the past papers. You have the solutions, all right? And then on Thursday, the 5th of December, right, we're going to have another revision session online that will look at any other issues people may have on the revision problem set and past papers. Okay, it's going to be recorded, but the only way you will benefit is if at the time you tune into it, you would have actually attempted something. Because what I'm interested in is hearing people's concerns or difficulties, not so much going over material and answering something that you haven't attempted as yet. You have the solutions anywhere. And just as a comment, I think Dr. Ringis might have mentioned this too for signals. The arithmetic and the algebra, the actual calculating of values is not so important as the approach, right? You get about 70% of your marks for how you approach the answer for the question, and about another 30% for actually getting a value in your answer. Okay, and unless we required, if you're calculating resistors and so on, you don't have to go to 2 and 3 decimal places and so on. Okay, you could round off the value easily and just give me an answer. And or if you have it just in the final form and it didn't work out the final value, leave it. Once the time has run out for that particular part of the question, go on to something else. Don't waste the time. Right? It's about 1 mark or maybe 2 for getting a final value. Okay, so you would have already had 80% of the marks, assuming that you were correct up to that point. Okay, so once the time, look at the marks, look at the questions, figure out how much time you need to spend on each part. When the time is up, move on to the next part. Okay, anything else? All right, so let me just stop the recording here for the time being.